All right, this video is meant to help you review and practice for the Unit 7 test on probability and statistics. On the test, you'll be responsible for knowing the basic rules of probability, so things like probabilities must add up to 1. You should be able to use a two-way table or a Venn diagram or create those yourselves given some data. You should be able to find probabilities that involve unions, intersections, this or this, or this and this. You should also be able to find conditional probabilities. Those are givens, A given B. And along with that, understanding the concept of independence and what it means for two events to be independent. You should also be able to make a tree diagram and use it to find certain probabilities. In terms of the symbols that you need to recognize and be able to use, first of all, A, right, is just some event. When we use a capital letter, could be like flip heads, or the sum of the dice is 5, or right, it's some occurrence that we want to happen. And so when we say P of A, we simply mean the probability that A occurs. When we say this symbol, what we mean is a complement, okay, which simply means not A. And so what we're asking for is the probability that A does not occur. So, if A was, eats breakfast, to use that example again. Okay, and then A complement would simply mean doesn't eat breakfast. Okay, so it's sort of whatever the event is, it's the opposite of that event. All right, this stands for union, but we can also say the probability of A or B, and that means either A happens or B happens or both, right? It's not exclusive. This would be the symbol for intersection, and another way to say that is P, A, and B. And so we need both event A and event B to happen at the same time. And then finally, P, A, given B. And we'll do examples with given probabilities, but again, we think of that as like we know B is guaranteed to happen or has already happened. So now what is the probability that A will occur? Okay, so you should see these symbols. You should know how to read them, say them in your own words, and calculate them. And so let's look at an example of some basic probabilities first. Okay, two different examples here. The first one, kind of like a homework example you had, you roll 2 4-sided dice. What is the probability that the dice will add up to 4? Now, you could do this with some, you can multiply some probabilities and things, but perhaps the easiest way is simply just to write out the sample space. Okay, kind of like you did on the homework. It does take a little bit of time, but it will get you the answer, right? It's sort of a brute force way to get there. And you want to think about all the different combinations, right? 1 and 3 is different than 3 and 1. Those are two different ways to get the same outcome. And in fact, those are two of the outcomes we care about, right? We want the dice to sum to 4, so that is one way that can happen. That's another way that can happen. And then we just want to make sure we get all of them. Okay, there's one other way that can happen, which is both of the dice come up with a 2. And so we want to consider how many different probabilities are there, or different possibilities are there. Okay, there are 16 possibilities. And as long as we assume the dice are fair and all of that, right, each of them are equally likely to occur. So that means each one has a 1 in 16 chance of happening. And so, right, we simply add them up and get 3 over 16. Okay, so when you're finding probability, you want your desired outcomes over your possible outcomes. 16 possible outcomes, of those 3 of them are desired. Okay, you could also be given a probability model. Okay, that would be a table where probabilities are assigned to certain outcomes. And so here we have a table just listing the incomes, the yearly incomes of families in a certain town. What is the probability that a family will have a randomly chosen family will have an income more than 100,000? Okay, well that would be this and this, but we don't know what that is currently. So we need to use the fact that all probability always adds up to 100%. So we'll just simply say 0.21 plus 0.67 plus 0.09, and let's see, that's going to be 0.97. Okay, that means the remaining probability needs to be 0.03. And so, right, we would want these. So the probability that you choose a family at random and they make more than $100,000 is going to be 12%, or 0.12. Okay, this would be a little bit on the easier side. Getting a little more involved now would be something like this. Okay, so we are given that there are 200 students at a high school. Of those, 120 are female and 80 are male. 60 of the males are taking a gym class and 70 of the females are taking a gym class. And we want to summarize this information with a two-way table. So you need to think about, like, what are my variables here? Okay, gender is one variable. And then taking a gym class is the other. So we would think of, what are the two outcomes? Well, you're either taking a gym class or you're not. So let's start by building a two-way table. Okay, male, female, taking gym, not taking gym would be our things. And then into that, we want to fill out, first of all, we know there's 200 students total. Okay, so you kind of build this piece by piece. Okay, and then what are they telling us? 120 are females, so the total number of females and the total number of males. Okay, and then of those, 60 of the males are currently taking a gym class. So that, right, that's not telling us this part, right? It's telling us the males that are taking gym, male and taking gym. So that's going to go in this slot. Okay, and then female and taking gym goes right here. And that's enough information to fill in the rest of the table, right? If 60 of the males are taking gym, that means 20 are not. Okay, so we have to add up to the total. Likewise, that means 50 females are not. And then going down the column, right, 130 and 70. And of course, 130 plus 70 equals 200, so we know we've done everything correctly. Okay, so you should be able to both read a two-way table, but also create your own. And from this, we can make a Venn diagram. Now, to do that, we need to define two events. If we're just asking you to make a table, you could define whatever events you want, but on the next slide, I'm going to use M is male, so let's just go with that, and G is taking gym. Okay, so you would build your rectangle. And remember, every single person needs to fit somewhere in this picture. So I'm going to call the first circle M and the second circle G. And so in here, right, would be all the people that satisfy both events. Male and taking gym would be in the overlap. Well, so that's these 60 people. Okay, of those, now, right, this is all the men. So who goes here? Well, that would be the males that are not taking gym, right? They're not in this circle, so that would be these 20 people. Okay, likewise, who would go over here? Well, that would be all the people taking gym that are not male, so the 70 females. Okay, but then what do we do with the 50 that we haven't used yet? Well, those are all the females that are not taking gym. They don't go into either circle, right? They don't fall under either event. So we usually just put them down here. It really doesn't matter. Anywhere in the rectangle would be fine, but usually we put it in the bottom corner. Okay, and the idea is you've represented everybody in this population as either belonging to this circle or not. Once you have that table, or once you have that Venn diagram, you should be able to find some probabilities. So you may want to pause the video right now and just try these. See if you can find these given probabilities. Right, so first one, fairly straightforward, right? What is the probability that you choose a male? We just choose one student at random. I should have said that. We choose one student at random. Okay, well, so there are 200 students to choose from. 80 of them are male. No, I mean, that's the answer, but we can reduce that, right? That's going to be 8 out of 20. So 8 out of 20 reduces down to 2/5. I should be able to do that in my head, but I'm lazy right now. Okay. Straightforward. Okay, again, some students find it helpful to write it in words. So we say union, but if you want to say or, what is the probability that you are male or taking gym? Okay, well, we have to consider all of these people, right, are male. All of these people are taking gym, but we have to be careful. We don't want to just do 80 plus 130 because we would accidentally be double counting these 60 people. So it's probably just easiest to just add up the numbers, right? 60 plus 20 plus 70 is going to give us 150. Okay, or you can think of it as, right, that would be 1 minus this probability, right? It'd be 200 minus the people that are not taking gym and are not male. That's another way to think of it. Either way, you end up getting 3/4. Okay, and decimals are fine for these. Use a calculator, of course. Either way. This one here, right, this means and then this, right, so G complement would just mean not taking gym. So male and not taking gym would be these 20 people. Okay, so you're looking for a place where both things are happening at the same time. So 20 out of 200, or of course 1/10. Okay, those are what we did in Unit 7.2. In 7.3, we started to talk about given probabilities. So this is male given that they take gym, and this is gym given that they are male. And I put both of them here just to show you that they don't necessarily come out the same, right? So the order does matter. And so what we mean is, right, given that we know the student chosen at random is taking a gym class. So that is not something you have to guess or wonder about, like you know for sure. What is the probability that you're going to pick a male? So think of it as like you go down to the gym, right? And you're looking at the students that are taking gym class. Well, so that would be these 130 students, right? These 70 wouldn't be there. They're not in our population anymore. We're not worried about them. And so the probability that you pick a male, given that you know they are taking a gym class, is going to be 60 out of 130. Okay, so you can think of it as you are restricting yourself to just this column of the table. And of course, that reduces to 6/13, okay, or as a decimal, it's about 0.462 if you round off. Okay, just round to 3 places on the test if you could. Right, but then it is different if we ask gym given male. Okay, so now we are saying given that the student is male. Well, so that means these students, right? These 80 students. And again, it's like limiting ourselves to just one row or column of the table. Of those, how many are taking gym? Okay, 60 out of 80. So you end up getting the same 60 people, but the probability is out of a different possibility, right? So 80 students are male versus 130 are taking gym. And of course, that's 3/4. Okay, so the order matters. You should be able to find these probabilities. You should also be able to do it with a Venn diagram, but it would be sort of the same thing. All right. From here, you should also be able to decide if two events are independent. So the definition of independence just means, right, two events are independent if one happening has no effect on the probability of the other. Okay, in other words, if we know that one event has happened, that doesn't change the probability that the other event is going to happen and vice versa. And so mathematically, we can say, right, if M and G are independent, that would mean the probability that you choose a male is the same as the probability that you choose a male given that you've chosen somebody in a gym class. Saying that one more time, in other words, knowing that someone's in a gym class doesn't change the probability that they're male. If they are independent, that will be true. So the question is, are those equal? And so we would go ahead and check. Now, of course, on the previous slide, we already found these. probability of male, we said, was 0.4. And the probability of male given Jim was 0.462, approximately. Well, those are not the same. Because those probabilities are not the same, these events are not independent. Okay, so somehow, knowing that our student is taking a gym class increases that probability a little bit. Okay, so there's an effect. Knowing one thing has happened has an effect on the probability of the other. If, let's just say, it did come out to, you did get 0.4 equals 0.4, you would need to check the other arrangement. And by the way, you could have set it up like this as well. You could have done P of G equals P of G given M. If it's independent, both of these have to be true. So you would need to check both. But as soon as if you check one and it's not equal, you can stop, because at that point you know they can't possibly be. Okay, you can check either one. If it's going to be independent, you need to check both. And they both need to work. All right, to give you an example, an event that is independent, all right, let's consider this. We have some bag, and I'll draw a picture here just to visualize. We have a bag, and in that bag, we have a bunch of marbles. Some of them are red. 5 of them are red. 2, 3, 4, 5. 4 of them are blue. We have colors. Let's use them. 1, 2, 3, 4, and 3 of them are green. And let's just say you can't see in the bag, and you're just going to shake it up and choose something at random. Okay, so you choose a marble from the bag, you look at the color, you write it down, but then you put it back into the bag, you shake it up, and you draw a second marble. Okay, so these are independent events. Okay, assuming you shake up the bag enough, and you're not looking in the bag, and you're just you're choosing a marble at random. If I pick a red marble and then put it back and shake up the bag, the chance that I'm going to choose a red marble doesn't change, right? The bag has no memory. So you could draw, in theory, you could draw 10 red marbles in a row, and then you would be just as likely to draw a red marble on the next chance. So what is the probability of first drawing a red marble and then drawing a blue marble? Okay, we said for independent events, P and B is simply probability of A times the probability of B. Okay, but that only works if we know the events are truly independent. And so all we need to do, right, what is the probability of red and blue? And we'll just say, to keep this easy, in that order, right? First a red marble and then a blue marble, is we simply need to find the probability of red and multiply that by the probability of blue. Okay, so looking at our bag, right, 5 plus 4 is 9 plus 3 is, there are 12 marbles total. And so the probability of drawing a red marble is 5/12, and the probability of drawing a blue marble is 4/12. Okay, and so we simply get, we could reduce this to 1/3, and that gives us 5/36. This is, quote unquote, easier because the events are independent. However, considering the same situation but changing the rules a little bit, right? What if we draw a marble from the bag, but then we don't put it back? Okay, so we draw another marble without replacing the first. Okay, this is no longer independent, because once we pull a marble from the bag, now suddenly, right, go back, like we go ahead and let's say we do pull out a red marble. Okay, well, now that red marble is no longer in the bag. And so now there are no longer 12 marbles, right? There's only 11 to choose from, which is going to slightly change the probability of drawing another red marble or drawing another blue marble or something like that. Okay, so in situations like these, although you can certainly just think your way through them, it can be helpful to make a tree diagram. So we're going to do that. And on the test, we'd probably ask you to make the tree for this. Okay, so there are two events here. your first draw. Sorry, it could be 3 colors. Your first draw could be a red marble, or a blue marble, or a green marble. And from there, right, you could draw red, blue, or green, red, blue, or green, red, blue, or green. And there's a lot of different outcomes here, but the tree is going to help us to organize those probabilities, right? So we go back to our bag, right? On the very first draw, there are 12 marbles to choose from. So each of these is going to be a probability out of 12. And then we know there are 5 red marbles, there are 4 blue marbles, there are 3 green marbles. Okay, so we can fill those into those branches. And then from there, right now, once we've drawn a marble from the bag, we know each of these will be over 11. And this will get a little tight, but each of these will be a probability over 11 because there are only 11 marbles remaining. Okay, well, so right, we think of when you've gone down this branch, it means that event has already happened. So if you're here, it means you have drawn a red marble. So now think about, right, think of the bag loses a red marble, so now there are only 4 remaining. Okay, so the probability of drawing another red is 4 out of 11. There are 4 red marbles to draw. You didn't change the number of blue marbles, there are still 4. Okay, you didn't change the number of green marbles, so there are still 3. Okay, likewise, you can fill in the rest of this table. So if you've drawn a blue marble, okay, now there are only 3 blue marbles remaining. There are still 5 red marbles. There are only 3 blue, and there are 3 green. And then likewise, if you've drawn a green marble, okay, now there are only 2 remaining. And so there are still the 5 red and the 4 blue. Okay, so the tree gets a little complicated, but it helps you organize now questions like these. What is the probability that you first draw a red marble and then a blue marble? Okay, well, you would multiply down the branch. Okay, so we said that the probability of A and B is the probability of A times the probability of B given A. Okay, well, the probability of red given blue given red rather is this 4 11ths, right? This takes into account the fact that you've already drawn a red marble. So when you multiply down the branch of the tree, that's what you're doing. Okay, it's just doing that probability for you. So we would simply say 5/12 times 4 11ths. Okay, and what does that come out to? 20 over 132, which that reduces, but we'll just leave it. Okay, for the first question, using the tree diagram might have been a little bit of overkill. You could probably come up with this yourself without needing a tree to do that. But answering a question like the second one would be where a tree would be really helpful. Right? What is the probability that you draw at least 1 red marble? So at least 1 red could mean also that both are red. And so what you do in that case is you add up all desired branches. Okay, so in other words, maybe I'll use a different color to highlight this. We want to consider all the paths down the tree that will give us at least 1 red marble. So that would be this path, right, with 2 red marbles, but that would also be this path and this path, because we would have drawn the first marble being red. Okay, but then we'd also have this path here, blue and red, as well as green and red. So there are 5 different ways that could happen. And what you would do, and we don't have to go through all the math of doing this, the calculator could do this for us. Okay, but the setup would be the probabilities of all those branches added together. Okay, so 5/12 times 4/11, that's the probability of drawing both reds, right? This first branch, plus 5/12 times 4/11. Now we end up doing the same probability, but that's a different outcome. That's red, blue. And then 5/12 times, it's hard to see now, but 3/11 was originally how we found green, plus 4/12. Okay, now we're going down the blue branch, plus, and now we're going down the green branch. Okay, so we would consider all the different tree branches that would get us to that desired outcome and add up those probabilities. Working with independence a little bit more. Okay, so a worker is inspecting products on a line. There's a 2% chance that a given product will have a defect, and we will just assume that defects happen independently. So one product being defective does not make it more likely that another product is defective. Okay, what is the probability that a batch of 6 products will not have any defects? Okay, well, this is going back to our basic rules of probability. If there's a 2% probability that it will have a defect, that means there is a 98% probability that it will not have a defect. And so what we are asking is the probability that the first is fine, has no defects, and the second is fine, and the third is fine, and so on and so forth. But because these are independent events, that simply means we can multiply the individual probabilities together. And so we will simply say 0.98 times 0.98 6 times, or of course, we can just say to the 6th power. Okay, take our calculator, multiply that out, and we get 0.886 if we round off. Okay, so there is an 88.6% chance that you will have 6 products come down the line and none of them will have any defects at all. Okay, one last example here. It's a little bit more challenging. Building a tree diagram given some probabilities. Okay, so we have a chess player. If you don't know, in chess, right, there are white pieces and black pieces. And usually you flip a coin or roll a die or something to decide who's going to play which. Generally, there's an advantage to the player playing white because they get to go first. So, we have some chess player here. The probability that they play the white pieces is simply 50% because we're flipping a coin. And then you have to understand the difference between these two expressions. So when it comes to a tree diagram, the probability that they win given that they play white is 0.61. And the probability that they play black and win is 0.225. And we want to know at the end of this question, what is the probability that the player will lose a randomly chosen match? And so this is another example of where a tree diagram is helpful. So first of all, we just need to decide, are they white or black? White or black. Okay, but in this case, that's just a 50-50 shot. And then, of course, right, you could play the white pieces and win, or you could play the white pieces and lose. And same thing for playing the black pieces. Now, there's a difference between what these mean. Okay, when we're giving you the given probability, what we are doing is we are telling you the probability that goes on the branch itself. So the probability given that you are playing white, okay, again, remember from our marble example, given that you've drawn a red marble, right, means you're at that place on the table or on the tree. So given that you are playing white means you are here, and now you're deciding, do I go here or here? So the probability that you are going to win is 0.61. That goes here. And well, that means the probability that you're going to lose is 0.39, right? They must always add up to 1. Any individual part of the tree always has to add to 100%. Okay, differently now though, play black and win. Okay, so when you use the word and, it means you go down the branch and get the final answer. So what we are saying is, if you take this probability times this probability, it is going to equal 0.225. The chance that you play the black pieces and you win is going to be 22.5%. So to figure out what goes on the branch, you need to work backwards. Okay, so we know it's 0.05 times something. We'll just say x is going to equal 225. Okay, take your calculator and divide 0.225, divide by 0.5. Okay, you end up getting 0.45. So that is what goes on the tree, right? The branch itself. So you need to understand the difference between those two notations. Okay, and then this, of course, means there's a 55% chance you lose. So now the question is, what is the probability that you will lose? Well, there are two ways you can get there, right? You can either play white and lose, or you could play black and lose. So again, you calculate the individual branches and then add up those results. So I'll just tell you what you get. 0.5 times 0.39 plus 0.5 times 0.55. You get about 0.47%. Okay, so it's important that you really need to know the difference between and, or, given, complement. Okay, you need to understand all of those different symbols. This is certainly not everything, but it is a broad overview of the skills that you need. So of course, if you need more, email your teacher, me, Mrs. Oñate, Mr. Jordan, whoever it is. Let them know what you need. Let them know what extra practice you need, whatever. They'll be glad to help you. I will be glad to help you. Otherwise, have a great day.